Okay, welcome everyone. This evening, first of all, I'm Ramy Rashad. I'm currently a PhD at the, I just finished my PhD at the University of Twente. Oops. And I'm now a postdoc at the Robotics and Mechatronics group. Originally, I'm from Egypt, so yeah, kind of guess I'm not European. So in this presentation, first of all, you've got a lot of information in the previous talk, so I promise to keep this one a little shorter. That's the first thing. And the second, it will be more broader in the sense that I would really like to give you more of a summary of about, I think, 120 years in like 20 minutes. So it's a little bit challenging task. But the goal of really this this summary or this quick glimpse through the history of UAVs is to get a lot of learned lessons. So there are a lot of things that are just common for UAVs, unmanned aerial vehicles, slash drones, slash aerial robots. All are interchangeable terminology. And there are a lot of things that are also general to technological development in general. Okay, so that's really the reason I chose this talk for you. Okay, so let's start. So aviation really started a very, very long time ago, and people were very much inspired by birds, right? So just find flying birds, flying creatures, and then just they want to create machines of their own and start conquest the skies. And as you know, so the first really successful flight was by the Wright brothers in 1903. But before that, actually, so what the Wright brothers did was a stepping stone for humanity, right? So it was really one of the biggest milestones ever, really, to conquer the skies. But actually, this quest actually started much earlier than that. So really, about 100 years earlier, with a lot of people actually trying to mimic the flapping behavior of birds, right? So one of the earliest attempts actually of building wingsuits was by Abbas ibn Firnas in Andalusia. And a lot of people actually, not just Abbas ibn Firnas, really wanted to build flying suits. And they had the expectation of something like this, right? So this was their expectation, that they would have something similar to birds. They would fly and then they would start to glide, right? So just not actually with a controlled flight, just maneuvering and then enjoying the view. But actually what happened in reality is this. So this is in 1912, one of the attempts in Paris, someone actually building a wingsuit and trying actually to jump from the Eiffel Tower. And yeah, the results was not very promising. It's a little bit disturbing, so actually I'm gonna stop here. Okay, so you can imagine what happened next. So this was the first attempt, really. So just building wingsuits. Then people start, okay, now maybe let's not build wingsuits. Maybe let's do ornithopters, right? Where ornithopters are just a general term for flying machines, right? So for flapping machines. Okay, so any machine that just flaps like a bird is called an ornithopter. And the first attempts was by Leonardo da Vinci, and actually a lot of sketches were found in the beginning of the 16th century, try actually to replicate a flying machine. And as you know, what happened after so many years, about 400 years later, actually the Wright brothers converged. But actually the key point that I want to highlight here is that actually humanity did not converge to actually flapping wing flights, right? So although this was the inspiration, they converged to another completely different solution, right? So the solution that this was about fixed wing aircrafts, right? So this is the most widely used aircrafts. That's if you flew a plane, most likely then this is the type of plane you flew before. Okay, so this was a quick glimpse of this before what happened before the Wright brothers. Okay. Now, what happened next is that, okay, ever since the Wright brothers flew, the fixed wing UAVs became evolved at a very, very high rate. Unfortunately, because motivated by their hostile capabilities, right? So you can imagine that it only took 11 years for powered aircrafts to become an important branch of the armed air force in World War I, right? Initially, airplanes were not enough to do actually like combat in the sky, but actually they were only used for reconnaissance, just like flying eyes in the sky. But by the end of the war, so just 4 years later, it was enough that there was a division of the army called the Air Forces, and it included fighter and bomber aircrafts as well, right? And the capability of aerial vehicles, right, they triggered a massive amount of military funds, right? So the military just put a lot of money, allocated them for the development of this technology. So this was a very, very new technology, right? So if we go back, so the first plane that ever flew was 1903. Now we're talking only 11 years later, right? So this is in the history of mankind, this is very, very little period. But because of all of this money that was put into this development of this technology, fixed-wing aircrafts were evoluted at a very, very high rate. And just to give you a glimpse of how fast this evolution was, so at the beginning of the war, so the maximum speed of the aircrafts was only 80 kilometers an hour, right? By the end of the war, right, it was 240 kilometers per hour. So 3 times it was advancement during the war. So you can imagine how much money was put just to get these results. Okay. Another remarkable thing that actually I find very interesting is that actually the first UAV, so the first unmanned aerial vehicle, was developed in 1917, right? So only after, so only 11. So first of all, before the war was done, and the First World War was finished in 1918, and this, if you calculate, this was only 14 years since the first even aircraft flew, right? So you imagine that this drone flight that was called the Heutzsperre, right? It was flying all by itself without any human on it. So this is an incredible achievement. Okay. There is something about the fixed wing UAVs is that they were very suited for the military purposes due to their high endurance, right, and long range capabilities. So a typical aircraft could really cover a lot of ground, but there was just one simple capability that was missing in these crafts, which was what's known as vertical takeoff and landing, right? And for that, the airplanes, fixed wing airplanes, they cannot land at any place and they cannot take off from any place. So they need the long runways. And these runways, it's not always pleasant, right? So yeah, hopefully you always attended successful flights, otherwise you wouldn't be here. But actually, there has been a lot of crashes, right? So if the airplane does not manage to get actually it right to land, this is something very normal to happen. And usually what happens is that fixed wing aircrafts, they have a minimum speed. They cannot go much slower than a minimum speed. And that's why it's very hard actually to fly until you reach the ground and again reach this minimum speed. And if you don't just get it right during the runway's length, you have to crash, right? So this is also typical if you don't get if you have a finite length of the runways. Okay, sorry just for the disturbing videos, but just to get the message right. Okay. So all of these capabilities, right? So these were missing capabilities in fixed wing aircrafts, and this led to the like invention of rotary wing aerial vehicles, right? So the first successful flight of this, for example, this you see here in this figure on the left, it's a helicopter, right? So it's more of a quadrotor, what people know nowadays of a multi-rotor vehicle. And this was the first flight in 1920. And after that, only by 39 years later, the first unmanned aerial rotary wing vehicle was actually successfully deployed, right? And you can see that actually this aircraft here on the right, it's actually flying in a very, very, very difficult situation where it's actually trying to land and actually take off from on a ship in the sea, right? And this is completely impossible for conventional fixed wing aircrafts, at least at that time. And that's why this was the main reason, right? So this is the capability that is very, very unique to this kind of UAVs, right? So there's the vertical takeoff and landing, and also something that's called hovering, right? So these kind of vehicles, they can do hovering. Fixed wing UAVs, they can never do hovering, right? And by hovering, I mean just stand still in the air. Okay. There's another type of aircraft, which is actually what started in the first place, which are the flapping wing aircrafts. Okay. So you can imagine that if already people had the fixed wing UAVs and multi-rotor vehicles successful, no one would actually think about flapping wing UAVs, and that's right. So they were really abandoned for many, many years, and they were actually considered by many people like a futureless technology. And the main reason is that they are much more complicated compared to fixed wing UAVs and rotary wing UAVs. And just to give you like a glimpse of the numbers, right? If you remember the numbers that I was just mentioning, so I imagine that the first fixed wing aircraft it took off in 1903, and the first unmanned aerial vehicle of a fixed wing type was in 1917, right? So it took 14 years to develop the first drone, as we call it in these days, right? For rotary wing UAVs, it took 39 years to develop the first drone, right? Whereas for fixed wing, for flapping wing UAVs, it took them 45 years to get the first UAV, okay? So these numbers actually give you a glimpse of actually how complicated it is to actually fly a flapping UAV or a flapping vehicle in general compared to a fixed wing vehicle in general, right? So one of the take-home messages: if you find a flapping wing UAV and it's a taxi or something, don't drive in it. Just go for the normal fixed wing option. Okay, it's much more safe. Now you see that, okay, this was really just a quick glimpse of the history. And actually, one might ask, why would actually someone really go back to flapping wing UAVs or flapping wing vehicles when they already had very successful fixed wing and rotary wing vehicles? And the reason is really just people were inspired, right, by birds. So it all started by birds, and people really loved the idea of actually just mimicking birds, mimicking flying creatures. And it's just an inspiration for so many people. And that's why a lot of individual visionaries, not worldwide projects, were just kept on doing their own thing, doing their own research on just developing new types of wings, new types of aircrafts, flapping wing aircrafts. And you see that the first one actually flew in 1942, and the first UAV was in 1991, okay, just 45 years later. Okay, so this is UAVs in the past. Now, where are we, right? So how fast or how well are drones these days? There are three things that you can find about drones these days, right? So in all of these different categories, right? So fixed wing UAVs, rotary wing UAVs, and flapping wing UAVs. You can always see some trend going, and the first trend is that drones are getting smarter, right? They are getting smaller, and they are getting closer to people, right? So the old types of fixed wing UAVs, right, they're only used for military, right? And now they are much more smaller and available cheaper vehicles that people could use for whatever applications, right? And same goes for rotary wing UAVs, and this was never possible except with all of the advancement that actually happened in other fields. So complementary fields to UAV, to the field of aerial robotics. For example, like miniaturized sensors, so like MEMS, micro electromechanical systems, microprocessors, all of these advancements that happened in this field. The advancement that happened in electric drives that made them actually very small, that actually made it possible to develop a high power to weight ratio of electric drives. The advancement that happened in batteries, all of these advancements in other fields, not in UAVs, that actually have led to the downscaling of UAVs to this extent that you see in this field. Okay. Another thing that also made it possible, another field that was completely complementary, was the robotics community, right? So by the robotics community, I mean the people that are just working on perception algorithms, planning algorithms, decision-making capabilities, for example, that all fits within the artificial intelligence paradigm. All of these people that actually developed all of these algorithms that have made actually all of these drones possible. And most of these drones now are just, they have some sort of autonomy in it, right? Just as a small example, all of these rotary wing UAVs, they have a capability that they have a property that actually they are inherently unstable. And by that, I mean, if you turn off the propellers of rotary wing UAVs, they just fall from the sky. There's no way that they could fly with the propellers off. This is completely different corresponding with respect, for example, to fixed wing UAVs, right? Fixed wing UAVs, even if the propellers turn off, right, and people just get scared, and in a commercial aircraft, the airplane could still fly completely without the propellers, without the turbines, and it just could just as a glider try to land, for example, in the water, right? Which is why fixed wing UAVs are much safer than rotary wing UAVs. Okay. Now there's something about the flapping wing UAVs, right? The properties of flapping wing UAVs is that the best thing about it is that it takes the best of both worlds, right? So the flapping wing UAVs, they actually have some sort of almost vertical takeoff and landing, right? You can already see it in birds, right? They don't need a long runway to actually take off. They could like jump and already start with a little bit of incidence angle, try to fly. So they combine the vertical takeoff and landing capability. They also have all of the nice characteristics of actually fixed wing UAVs, right? So if a bird or a flapping wing UAV just stops flapping, right, and just uses its wings as a fixed wing UAV, then you have all of the long range and endurance of fixed wing capabilities, right? Which is why people are still interested in these kinds of vehicles. And actually, there's a lot of advancements, both technologically and also from the aerodynamic perspective, to try to understand how to actually develop these birds. I'll come back to that later. Okay. So this is the first thing that you see about the UAVs today, right? Compared to back then, they are smarter, smaller, and closer. Another thing that you see, and it's proven by Abhijay's talk from a while, that UAVs are really expanding in the civilian market, right? So I already showed you that the drones, they actually came out as a technology from the military. Unfortunately, just like any other technology that we're using nowadays. But actually, because of the small scale and the low cost of the current aerial robots, a lot of people have already, especially in the civilian market, a civilian sector, they started to actually make use of these drones, right? So historically, as I shall show you, the military applications were the main driving force for developing the UAV technologies. But now actually the market share of civilian applications is increasing at a very, very high pace. Just to give you just some numbers. So according to some market predictions, right? So the commercial unmanned aerial systems market, right? And by unmanned aerial systems, I mean the UAVs themselves, like the vehicles themselves, and also any auxiliary equipment, for example, like any electronics that's, for example, on the ground stations, for example, any monitoring equipment, any sensory equipment, all of these stuff are just auxiliary equipment. So actually the commercial unmanned aerial systems market is expected to increase from $5 billion in 2019 to $14.5 billion in 2028. Okay. So this is really in like 7 years time that it would really boom and expand that much. Okay. And these numbers actually, they have a very important message that actually, it says that actually the civilian market is no longer just something secondary with respect to the development of these UAVs. It's actually becoming as important, if not more, as a driving force than compared to the military applications. Okay. And just from what Abhijay showed you in a while, the applications are numerous, right? So, for example, one of the nice potential applications that you all mentioned in the discussion are actually happening right now. So those are not actually still stuff to be done in the future. For example, you can see here on the right, top right, this is actually an air taxi that's developed by a Chinese company called Ehang, and it's actually doing flights as we speak. Okay, so this is actually now it's operational. DHL and Amazon, for example, and other logistic companies are actually developing drone package deliveries. Domino's Pizza already started testing some of these applications, these services. Inspection, for example, and maintenance of any hard-to-reach sites, for example, like wind turbines, like power cables, pipes, and so on. One of the actually biggest market sectors of UAVs is actually entertainment, right? So just go to Media Market or any other store, just buy a drone for fun and just fly, right? So this is really a big part of the sector. And disaster responses, for example, or doing really scientific, using it as a scientific equipment, right? For example, to take samples from inside of volcanoes. All of these are applications that are happening right now. And there are many more awaiting to be discovered, okay? So this is just in a very, in a nutshell, really. UAVs then, UAVs now, today, and I want to just tell you something about UAVs tomorrow, right? So what's the future of UAVs? What do you think, how it's going, right? So what I just show you is that one thing to take as a take-home message is that the aerial robotics is an interdisciplinary field, right? And it requires a lot of fields to be actually, a lot of knowledge different from different fields to actually just build the drone and get it operational. And it's also evolving and progressing at a very high rate, okay? And as a result, there exists a wide range of emerging research directions nowadays, right? That are hardly classified or even counted. And out of these many different emerging fields of research, two of them I like very much, and I'm working personally in them. The first one is called aerial physical interaction, right? So all of the previous applications, for example, all of them that I've showed you in this slide, and also the ones that Abhijit was talking about in the beginning, use the drones as a flying sensor, right? So the goal of the drone is just to have a sensor on it, for example, like a camera, and then you just use it to do something without actually touching the environment, right? Now, what researchers are working on, and it's a very active field of research, is that we want to extend the applications of UAVs, right, to be able to use them not just as flying sensors, but also as flying manipulators, right? And there are so many approaches to do that. Actually, one thing is, for example, to put a robot arm on the actual drones that are already flying. For example, you see this is, for example, a very heavy KUKA arm, and it's put on this extremely large scale multi-rotor. For example, these are all experiments done, for example, inside of the lab. This is an experiment done to actually do contact-based inspection to pipelines, right? And for example, this is one of the work that I've been doing here at RUM at the University of Twente. And you see here that we've been able to actually just develop this new drone and develop algorithms that actually allow it to push on the wall, right? And actually this pushing is the most difficult part. After the drone is able to push, it can do so many things, right? So the basics of many of these applications is that we need to make drones able to push on something, right? Interact physically with it. That's the main challenge. And here, the end effector, the tool that it's using is just a pen, and it's writing whatever you want. And it's writing the initials of our lab, right? The robotics and mechatronics lab. Okay. So this is one of the very nice applications of drones, the future applications, and a lot of people are working as we speak for developing these technologies. Another thing that I'm also personally interested in is bio-inspired robots, right? So going back to the same old fantasy of actually building flapping wing UAVs, right? This is still a very active area of research, right? That it's not just about the challenges that it poses, actually, and this is something very nice for research, right? So just as a take-home message, if you're working as a researcher, don't work in something that the industry is working in, right? Always find a sweet spot that's very at the top, I would say like top tech problems, or really very hard problems that actually the industry cannot solve by themselves. This is really where the sweet spot of researchers, especially highly educated researchers. Now, these kind of applications, right? So the birds, they are not just inspiring, they are very intriguing in the sense that they could do stuff that are much difficult than actually what we can do with all of these drones today, right? For example, just to give you a glimpse that these birds are actually having flexible wings, right? And from a theoretical point of view, these flexible wings are infinite dimensional, right? So they can have much more difficult shape. They're not just finite dimensional. They don't just have a finite number of degrees of freedom. They have an infinite number of degrees of freedom, right? And they do that, and they fly, they perch, they change. This is actually not a Photoshop. This is actually an actual photo of a goose that's actually flying inverted. Okay, and this is something that the birds, they do just completely naturally, and in so many ways this is a big challenge. So this is a challenge for engineers mechanically. This is a challenge aerodynamically to understand what's the aerodynamics that's going on there to actually for the birds to be able to do that. There's also the challenge of actually developing control algorithms, right? So the control algorithms that are for fixed wings are different from the ones for flapping rotary wings. And they are completely different from the ones that are used by flapping wing UAVs, right? So all of these are just challenges again and again and again. Just they trigger a lot of enthusiastic researchers to try and understand the aerodynamical, the structural, the behavioral patterns of natural birds, and then use that to actually try to develop, first of all, abstract these understanding, right? To develop features, and then develop robust and high performance flapping wing aerial robots, right? And this is also what you've probably seen some of these results before. This is the robot that actually developed at our lab, and actually came out, a spin-off came out of that. That's Clear Flight Solutions. It changed now into the robotic bird or rover. And actually, this is one of the most advanced results in the world, really, to develop this kind of flapping wing UAV. It's very robust and it could be used for a lot of applications, but still, even with this one flying, we've barely scratched the surface of actually understanding how flapping wings fly, how birds fly, and actually how to develop flapping wing UAVs. Okay, and with that, right, I would like to conclude my talk with some take-home messages, right? So one of the first important messages that I want to share with you is that when we talk about the industry, or when we talk about applications, or when we talk about impacting the society, there's a very important rule: the simpler, the better, right? So you see that, for example, that although people were triggered by all of the capabilities of flapping wing UAVs at the beginning, right, and they tried to design wingsuits, they tried to design ornithopters, it just did not work, right? So the simplest solution, which is just using fixed wing UAVs, was the best one, and was the most effective one, and it's what we use nowadays for as the most efficient and the most cheapest, the cheapest actual transportation means on the earth. Okay. Now, another thing that is also it's obvious, but it's actually it's very important, that actually funding is crucial for technological development. Right. The reason why flapping wings and rotary wings took so much time actually to being developed is that the military or the funding sources were not just interested in them from the beginning. If it was the other way around, if the first airplane that actually flew was the rotary wing UAVs, then we would have now that the standard for flying is actually rotary wing UAVs, right? So it really depends on the funding. So whenever you find that a lot of source or a lot of money are being put in a project and it's just to develop a technology, know for sure that it will happen, right? So this funding is crucial. And as a researcher by yourself, it's very limited that you can do without all of this funding. And actually, if you choose to be a researcher yourself, getting funds and getting grants it will be part of your daily job. Okay, so this is really something to keep in mind. And I would say the best thing about this point really is that nowadays there are new ways of getting funding actually for your projects or for doing research. Some ways are, for example, are actually building companies, right? So going as an entrepreneur yourself and being your own boss and actually funding your own ideas. This is also something that a lot of the new generation is really taking it seriously. And it's actually something that's changing the applications as we know. Third take-home message is that UAVs, drones, are getting smaller, smarter, and closer to people. That's something. So it's just a matter of time we're going to have a drone at your house doing something for you, right? So this is it will happen soon. the civilian markets really boomed, right? So you can see that, okay, it all started from the military funding and it all started from the military application, but now the civilian market is taking over and there's just so many applications for UAVs in the civilian sector. So this is an active area of research, an active area of also of jobs. So you're going to find tons of opportunities in this field. And with even after all I presented and after all of what Abhijay presented, there are so many open questions and also challenges for future UAVs, right? So the development never ends, I would say. There will always be questions, there will always be research possibilities, and that's why this is actually good news for university students and university employees, right? Researchers in general, because there's always something to work on. There's always room for improvement. So with that, I would like to conclude and thank you very much for your time. And if you want to just for future collaborations or for if you want to get in contact about any of these topics and other topics, just you can follow me on LinkedIn or contact me on LinkedIn through Ramy Rashad. And this is my email address if you want to have any questions. Now I think we can open the room for discussions. Thank you very much.